The two limits we're going to do here using L'Hopital's rule are typical of the indeterminate forms where you have to rewrite first in order to use L'Hopital's rule. So let's start with the first one. It's not bad, but we always have to be careful. So I want the limit as x goes to 0 plus. You'll see why the plus is there in just a second. I want x times the ln of x. Just like that. Now, here's the thing is that I can't say the limit x approaches 0 because ln of x isn't even defined to the left of 0. Now what happens here? When x gets very close to 0, x gets very close to 0. That's not so bad. What happens to ln of x? Well, I'll just remind us what the picture looks like. The picture of ln of x looks like that, right? And so this piece right here is actually getting very close to minus infinity, whatever that means. Now the problem is, if someone says, well, I can figure this out, it's like, well, this is 0, and 0 times anything is anything. Well, 0 times any number is 0, right? Well, this is infinity. Infinity times any number is infinity. Well, not when that number is 0. This really is indeterminate. We just can't argue by sort of very basic principles about what the answer is going to be. So we need to rewrite this as a fraction so we can use L'Hopital's rule. But we do know it's indeterminate, and once it's indeterminate, L'Hopital's rule is pretty much the only thing that's going to work. Now the problem is, in order to write this fraction, I'm either going to have to put the x in the bottom or the ln of x in the bottom. I'm thinking x in the bottom is going to be easier, so what I'm going to do, just before I take the limit, I'm going to multiply this by 1 over x over 1 over x, like that. So I'm not taking a limit yet. I'm just rewriting this as a fraction. On the top, I'm just going to get the ln of x. On the bottom, I'm going to get, well, I'm going to write it as x to the minus 1 because I want to take the derivative, and I do want to see what's going on. As x, when x is a tiny positive number, we already looked at the graph of this one. We know this is huge negative. When x is a tiny positive number and I take its reciprocal, this is a positive huge number. And so we're finally in a L'Hopital's rule situation. L'Hopital's rule. So we tell everybody, hey, we are using L'Hopital's rule. We take the derivative of the top, we get 1 over x. We take the derivative of the bottom, we get minus 1 over x squared. So you go like this. I say x arrow 0 plus. And at least I get a limit that doesn't have an ln in it. There we go, now we can see it. What am I going to do with this? Well, I'm going to do what we did back in chapter 2. I'm just going to multiply the top and bottom by x squared before I take the limit, because I can't take the limit as it sits. So I'm just going to write equals limit x arrow 0 plus. Multiply the top by x squared, I get x. Multiply the bottom by x squared, I get negative 1. And now I can just plug in, and finally we get 0. That is a typical indeterminate problem where you have 0 times infinity. Because 0 times infinity can be anything, and it's really not that hard to find examples of whatever you want it to be. But that's example number 1. Example number 2 is we don't have to be as creative, but we have to do a lot of algebra and not ever make a mistake. But here's the problem. Hopefully I'll get through this. We'll see. This is example 2. Just another indeterminate problem. I'm going to say limit as x goes to 0 of e to the x over e to the x minus 1, all minus 1 over x, like this. Now, when x gets close to 0, the bottom here gets close to 0, and the top gets close to 1. So I'm getting close to 1 over 0. That at least feels like a big number. When I plug in numbers close to 0 here, I also get 1 over 0. So it looks like a big number here and a big number here. But you can take a big number and subtract a big number and get a big number. You can take a big number and subtract a big number and get a huge negative number. You can take a big number and subtract a big number and get something close to 0 or 1 or 100. There's no way to tell. This looks like of the form infinity minus infinity. And the minute I'm going to put that over here, it's not really worth anything, but it's a little flag that says, ah, crap, L'Hopital's rule is going to be the only way that works. Now, unfortunately, L'Hopital's rule only works on fractions, a single fraction. A fraction minus a fraction, It's no good at all. So what we need to do is get a common denominator. So I'm just going to get a common denominator real quick and see what we have to do with this. The common denominator is x e to the x minus 1. So what I'm going to get here, I'm going to get x e to the x, and then minus e to the x, and then plus 1 all over x e to the x minus x, like that. I'm hoping I'm writing this in the best possible way, but we'll see. And we'll see how I'm possibly going to have room. Anyways, when x gets close to 0, this is going to be 0 times 1 minus 0, so the whole bottom's getting close to 0. When x gets close to 0, that's going to be 0 minus 1 plus 1, so the whole top is getting close to 0. And at least we get to use L'Hopital's rule. So we get to put our little L hop right there. Now we have to take the derivative of the top. That's going to involve some product rule. So it's the derivative of the top. Oh, I'm sorry. It's the derivative of the... I'm now taking the derivative of the top. That's going to be 1 times e to the x plus x times e to the x. So all I did was take the derivative of that first part and then minus e to the x, right? So the plus 1's gone. And boy, that didn't feel like it helped a lot, did it? I now take the derivative of the bottom. That's also that starts with the product rule. So this will be 1 times e to the x plus x times e to the x, like that, minus 1 like that, and we're supposed to take the limit all over again, like that, assuming I did this right. Now let's see here. If I plug in, oh wait, I see 1 times e to the x minus e to the x. So I'm going to do that. Not sure that's going to help, but at least it's less algebra to look at. So I'm going to L-I-M x arrow 0. On the top, I just have x e to the x. On the bottom, I'm going to have x e to the x plus e to the x minus 1, like that. When I plug in 0, I still get 0 on top. When I plug in 0 on the bottom, I get 0 plus 1 minus 1, so the whole bottom is getting close to 0. So we get to use L'Hopital's rule again, or we have to use L'Hopital's rule. Take your pick. When I take the derivative of the top, I'm going to get 1 times e to the x plus x e to the x. On the bottom, I'm going to get 1 times e to the x plus x e to the x plus e to the x. And then we're supposed to try to take the limit all over again. Here we go. Now let's see here. When I plug in, let's put a little bracket here. When I plug in 0 on top, I get, I don't get 0 anymore, right? So no matter what happens, I'm done using L'Hopital's rule. When I plug in 1 on the bottom, I'm going to get 1 plus 0 plus 1, that's 2. And there's our answer. Right? And I want to go back to the very beginning. Remember, this is a huge number. This is a huge number. But in the limit, this one was only about a half bigger than this one, right? So you can really get anything.